So everything works, so we can start our lecture. Please don't hesitate to interrupt me with your questions. You may ask your questions either in Russian or in English, it doesn't matter. Okay, so far we have discussed the general principles of quantum mechanics and some mathematics needed to formulate these principles. And today we will consider, we'll apply our knowledge to explore a particular physical model called a harmonic oscillator. This will be our first quantum mechanical system where we are able to calculate an exact energy spectrum. Looking ahead, I can say that the spectrum will be discrete. So let us write down the title of the lecture. Simple harmonic oscillator. Simple harmonic oscillator. As you know, in classical mechanics, a simple harmonic oscillator is a mechanical system with one degree of freedom, and the Hamiltonian, as usual, given by the sum of the kinetic and potential energy. The kinetic energy is proportional to the momentum squared, while potential energy is proportional to the position squared. Here, the parameters m and omega stand for the mass and the frequency or angular frequency of the oscillator. It is clear that the energy of the harmonic oscillator being given by the Hamiltonian can take all the values from 0 to infinity. It is not negative. So all positive values are allowed and no one is forbidden. And the problem now, and are passing to quantum mechanical consideration, we need to replace the classical Hamiltonian with a corresponding Hermitian operator, H hat. And to construct this operator, we can apply the standard von Neumann rules. Basically, we just replace the dynamical variables P and Q with the corresponding Hermitian operators. We just put hats on these variables. And the result is the operator P hat squared over 2m plus m omega squared or 2 who hat squared. And the problem now is to identify the full spectrum of eigenvalues for this operator H hat. And in physical terms, these eigenvalues should be identified with the energy values measured in experiments, that is, with outcomes of measurements. And by the end of this lecture, we will solve this eigenvalue problem by making use only the canonical commutation relations for the operators P and Q. Let me recall that P commutes with Q to give H bar I. So we will identify the energy spectrum without reference to any particular representation. That's why some people call this approach the algebraic method. And to apply the algebraic method, we need some algebraic preparations. Well, mathematicians teach us that given the difference of two squares, say x squared minus y squared, we can always decompose this difference into the product of two factors, namely x minus y, x plus y. Our Hamiltonian up here has similar structure. Don't mind these numerical coefficients because they are dimensionful and in appropriate units where 2m is equal to 1 and m omega squared is equal to 2. These are just unit. Okay, the main difference is that up here we have plus, while down here minus. If we replace this minus sign with plus, then we need to put I, imaginary unit, in front of y in order for this identity holds true. And so that the factors becomes complex numbers, which are complex conjugate to each other. Let us apply this algebraic identity to our classical Hamiltonian. Okay, with this identity I can write it in the following way. H bar omega times A star, where A and A star is a pair of complex variables conjugate to each other, which are given by linear combinations of their dynamical variables P and Q. Specifically, A is given by P plus Im omega Q over square root to M H bar omega, and A star is a complex conjugate to A, is given by P minus Im omega Q square root of 2M H bar omega. So it is easy to check that multiplying these two complex variables A star, we get exactly our Hamiltonian for the harmonic oscillator. Okay. Now, upon canonical quantization, when we replace P and Q with the corresponding Hermitian operator, these variables A and A star become a pair of operators. Again, to construct this operator, we just put heads on P and Q. Now it is quite clear that the operator corresponding to A star is actually adjoint or Hermitian conjugate to the operator A, because P and Q are Hermitian operators, and applying the Hermitian conjugation we just change sign in front of I. So in the cycle I will denote this operator by A head dagger, just to emphasize that this operator can be thought of as a Hermitian conjugate to the operator A. Now, by analogy with the classical Hamiltonian, we can try to rewrite, to express our operator H hat in terms of this pair of operators A and A dagger. But we should keep in mind that these operators A and A dagger be given by linear combinations of non-commuted operators P and Q, non-commuted operators of Q needed to commute to each other. So the order in product can make a difference. So let us try both the possibilities. First, we can substitute A hat instead of A and A dagger instead of A star to get H omega A dagger. And this is equal to 1 over 2m P plus Im omega Q hat times P minus Im omega Q hat. And expanding these brackets, I can write 1 over 2m. P with P gives me P squared. Q with Q gives me plus m squared omega squared Q squared. And of course I have some cross terms. P times Q, Q times P, right? With common factor minus Im omega. So Agree? And I see that the first two terms give me exactly my Hamiltonian H hat. But I also have some additional term due to non-commutativity of the operator P and Q. So this term is proportional to the commutator, to the canonical commutator, so it's just a numerical factor. So I can write this as Hamiltonian H hat plus constant term, so-called quantum correction due to non-commutativity of P and Q, H bar omega over 2. Okay, let us try to change the order of operators A and A dagger. Let me write this operator in the opposite order. First goes A dagger and then A. The answer is clear without any calculation, because changing the order of operator is equivalent to changing the signs. We just replace plus with minus, minus with plus, and these changes in signs can't affect the terms p squared and q squared. They are the same. The only difference in this, in the last sign, here we get plus. So the result is given by the Hamiltonian H hat minus H bar omega over 2. Is it clear? Do you follow me? Well, Rex somehow. Say, oh, please ask your question. No, because when we apply Hermitian conjugation, we also inverse the order of operators. This operator is Hermitian, so we can affect to it by Hermitian conjugation. If I apply Hermitian conjugation, I get the same operator, right? Oh. More questions? Other questions? Okay, let's move ahead. So we get, finally, in such a way, we get two equivalent representation for our Hamiltonian. Let me write down them separately. So I can write H as a, okay, H bar omega A dagger minus H bar omega halves, or using their other order of the operators, I can write the same Hamiltonian in this way: H bar omega A dagger A plus H bar omega over 2. By the way, from these two representations, I can immediately reconstruct the commutator of the operators A and A dagger. Indeed, I can just equate these two representations, and dividing by the common factor H bar omega, I get that A times A dagger minus A dagger A, that is the commutator of A dagger, is equal to 1/2 plus 1/2. That is 1. That is 1, or unit operator. So for the operators A and A dagger, I get the simplest possible expression. Well, not the simplest. The second simple expression. The first one is just 0. Here it's not 0, it's just 1. But the unit operator, like 0 operator, commutes with all the other operators. Okay, and using this commutator for A and A dagger, I can compute more complicated commutators constructed in terms of the operator A and A dagger. For example, I can easily find the commutator of A with A dagger to the nth power, to the n. And the answer is n times A dagger to the n minus 1. It is quite easy to derive this equality to prove this formula by induction. The base of the induction is the case n equals 1. For n equals 1, this identity boils down to the original one. It produces the original one. Now suppose that it holds for some n, and let us make the step of induction. Let us consider the case n plus 1. Okay, I can write this n plus 1 as A dagger to the n times A dagger. And now I can apply the Leibniz identity for this commutator to write it as a sum of two commutators, namely A dagger to the n times A dagger plus A dagger to the n times A dagger. Okay? Do you agree? And now I apply the induction hypothesis. By the induction hypothesis, this commutator, the second commutator, is equal to n A dagger to the n minus 1 times A dagger. I get the total exponent n plus the first term, which is just, because of this commutator, just A dagger to the n. So simplifying this expression, I get n plus 1 times A dagger to the n. And we are done. In the following, we will also need the commutators of the operators A and A dagger with the Hamiltonian of the harmonic oscillator. And to compute these commutators, we can either use the commutation relation for A and A dagger combined with the Leibniz rule, or we can use these two representations for the Hamiltonian. Once again, let us multiply the first representation by A on the right. Then multiplying the second representation on A on the left and subtracting from the first one, I see that the first terms cancel each other after multiplication, and we are left with H A commutator. So subtracting these from these, I get H omega bar H bar omega A. And now applying the Hermitian conjugation to this identity, I can write the commutator for the Hamiltonian with the operator A dagger, which is equal to H omega A dagger. Notice this minus sign. There is no minus sign in this commutator because when apply Hermitian conjugation swaps the arguments of the commutator, bring an extra minus sign. So these commutators differ by sign. Hermitian conjugation. Okay, any questions, comments? Is it clear? Okay. Now we're ready for studying the energy spectrum of the quantum harmonic oscillator. And the first thing we will prove about the energy spectrum is that the energy spectrum is bounded below. And to prove this fact, we make an assumption, a natural assumption, that the energy spectrum of the harmonic oscillator contains at least one eigenvalue belonging to the discrete part of the spectrum. So our assumption, there is an eigenvalue belonging to the discrete part of the spectrum. In the formula I will denote the corresponding eigenvector by the same letter E. So I suppose that there is an eigenvector E such that H on E gives me the eigenvalue E times E, and the norm of the state E is equal to 1. This is my only assumption about the energy spectrum. And now using the second representation up here, second representation for the Hamiltonian, I can write this eigenvector equation in more explicit form as h bar omega a dagger a plus h bar omega half acts on E equals E times E, right? This is just an equation expressing the fact that E is the eigenvector of the Hamiltonian with the eigenvalue E. And now I take the scalar product of this equation with the bra vector E. Let's take scalar or inner product. This gives me h bar omega E a dagger a plus h bar omega over 2 E with E. And at this point it is convenient to introduce an auxiliary vector psi. Psi is just the result of applying operator A to the eigenvector E. So the corresponding bra vector is obviously given by bra E a dagger. We just apply the standard rules for Hermitian conjugation. So in terms of this auxiliary vector psi, as the first term in my equality can be written as h omega psi plus, since the vector E is supposed to have norm 1, I get h bar omega over 2 is equal to E. And since the norm of the vector psi is certainly non-negative, I conclude, I infer from this equality that the energy, the eigenvalue of energy, should be equal to or greater than h by omega over 2. So this inequality sets the low bound for energy spectrum. The admissible energy value should be greater than or equal to h bar omega over 2. It is also clear that the equality sign is only possible when the vector psi is 0. Equality sign implies that psi given by A on E is 0. So the operator A should annihilate the eigenvector E for the eigenvalue to be equal h bar omega over 2. On the other hand, if we have some vector E which is annihilated by operator A, then this vector is automatically eigenvector of our Hamiltonian with eigenvalue h bar omega over 2. Indeed, we just substitute this vector to the eigenvector equation because the first term, the operator A, annihilates E. We are left with E equals to h bar omega over 2. So this equation is necessary and sufficient for the vector E to belong to the eigenvalue h bar omega 2, where the minimum possible value of energy. Is it clear? Or should I repeat something? Okay. Now starting from the vector E, I can construct more eigenvectors for my Hamiltonian H hat. For example, suppose that vector psi is different from 0. Suppose that psi is different from 0. Then I claim that psi is an eigenvector of my Hamiltonian. Let us check. So I apply the Hamiltonian to psi, that is h hat a hat E. And now using the commutation relation for the operator H and A over there, up here, we can rewrite this ket vector as A H E minus h bar omega A E. But we remember that E is eigenvector of the Hamiltonian with eigenvalue E, so I can proceed as follows. That is E times A hat E minus h bar omega A E. So combining the terms, I get E minus h bar omega times A hat E. That is omega times psi. So I see that whenever the vector psi is different from 0, is non-zero, then it is an eigenvector for my Hamiltonian with the eigenvalue E minus h bar omega. Okay, but this is not the whole story, because now I can replace my original vector eigenvector E with the eigenvector psi, because this is also an eigenvector for my Hamiltonian with a definite value of energy. I can substitute it here and repeat my arguments. So I can replace A with psi, and then I conclude immediately that the vector A psi, if non-zero, it is an eigenvalue, it is an eigenvector for my Hamiltonian with the energy A minus 2h bar omega, and so on, so on forth. So, starting with the eigenvector E, I can construct a sequence, a string of the eigenvectors E, A hat E, A hat squared E, so ta-ta-ta, A hat N, E, with eigenvalues E, E minus h bar omega, E minus 2h bar omega, so on, E minus n h bar omega. It is quite clear that this sequence of eigenvectors and eigenvalues can't go indefinitely. Why? Do you know the answer? Because because the spectrum is bounded below, and each time when we apply the operator A to the eigenvector, we decrease the energy value by a fixed amount, by quantum h bar omega. And since our spectrum is bounded below, there should be some non-negative, some positive integer n, such that the vector a to the n on E is non-zero, but the next vector a to the n plus 1 acting on E 0, and so are all the other vectors in the sequence. Let me introduce a special notation for this extreme eigenvector. In the following, I will denote it by 0, by naught. So ket naught is by definition a to the n acting on E. And by definition, this vector is annihilated by the operator A hat. So its defining property is that A acting on ket naught gives 0. And as I have told you above, each vector annihilated by operator A hat is automatically an eigenvector of our Hamiltonian with the eigenvalue h bar omega over 2. So it is simultaneously an eigenvector of the Hamiltonian with eigenvalue h bar omega over 2. H bar omega over 2. So our assumption about the existence of an eigenstate E belonging to the discrete part of the spectrum implies the existence of the vector naught with a minimal possible value of energy. So the low bound for energy belongs to the spectrum of the harmonic oscillator. To the spectrum of harmonic oscillator. These are eigenvector. Node is usually called ground state. Ground state, that is state with a minimal possible value of energy. With a minimum value of energy, ground state. And later on we will prove that for most of physical systems, the minimum value of energy is non-degenerate. So the ground state is unique. As for the harmonic oscillator, and in this case, the minimal value of energy is reached for ground state, and it is equal to h bar omega over 2. By the way, we see that this value is non-zero, contrary to what we have for classical oscillator. In a sense, ground state of classical oscillator, that is state with a minimal value, that is with zero value, corresponds to the equilibrium state where classical oscillator is at rest. And we see that unlike classical oscillator, the quantum oscillator can't stay at rest. Its minimal value is different, energy value is different from zero. So it somehow oscillates even at the ground state. Okay, questions, comments? Okay, let us continue our lecture. Before the break, we discussed the action of the operator A hat on the eigenvectors of the Hamiltonian. And we found that this operator A takes each eigenvector either to 0 or to another eigenvector. Now let me consider, I would like to consider the action of the operator A dagger on the eigenvectors of the Hamiltonian. And I claim that these operators, A dagger, is a Hermitian conjugate to the operator A, acts in a similar way. That is, it takes eigenvectors to eigenvectors. Let us check. So suppose that we have an eigenvector with energy E. We apply the operator A dagger to E, and suppose this vector is different from 0. Now we want to decide whether this vector is eigenvector of the Hamiltonian or not. There is only one way to see this. Just apply the Hamiltonian to our ket vector. And now we can use the commutation relation for the operator, for the Hamiltonian and operator A dagger that we derived in the first part of our lecture, namely that operator A commutes with A dagger to the operator H bar omega A dagger. So using this commutation relation, we can rewrite our ket vector in the following way. We can write this as a dagger H on E plus the commutator of H and A dagger, which is given by H bar omega A dagger on E. Now, using the fact that the ket vector E is eigenvector of my Hamiltonian, I can combine these two terms to get E plus H bar omega times A dagger E. So I see that my ket vector A dagger on E is indeed an eigenvector of the Hamiltonian with an eigenvalue E plus h bar omega. It is worth noting that this vector I have started with, A dagger on E, may never be zero. It is always different from zero. It is always different from zero. The reason is very simple. We can use one of our representation for the Hamiltonian in terms of their operator n and A dagger. So let me apply the Hamiltonian to my ket vector E. And I can write my Hamiltonian as A dagger minus h bar omega over 2 on E. If operator A dagger annihilates ket vector E, then the action of the Hamiltonian, this is the action of the Hamiltonian, reduces to the multiplication of E by the constant factor minus h bar omega over 2. But we know that the energy spectrum of the harmonic oscillator is positive. So energy spectrum is positive. So my assumption that operator A dagger annihilates the eigenvector E leads to the contradiction. So this is impossible. This is impossible. So this state is different from zero, and as we have seen, it is an eigen. Then it is an eigen state of the Hamiltonian. Similarly, we can apply the operator A dagger to this eigenvector A dagger E, which gives me just A dagger squared on E, and this is again an eigenvector of the Hamiltonian with eigenvalue E plus h bar omega plus h bar omega, that is 2h bar omega. Now applying the operator A dagger once and again to the ground state of the harmonic oscillator, which we denoted by note, we can produce an infinite sequence of eigenvectors, namely the ground state, A dagger on the ground state, A dagger squared on the ground state, and so on and so forth. A dagger to the n up to infinity. And all these vectors are different from zero, and they are eigenvectors of my Hamiltonian. They describe states with definite value of energy. The ground state has energy h bar omega halves, 3 halves, h bar omega 2h bar omega, and in general n plus 1/2 h bar omega. And by construction, all these vectors are different from zero, so they are eigenvectors of my Hamiltonian. Actually, there is another way to convince ourselves that all these vectors are non-zero. We can just compute the norm of these vectors. Let's do this. Let's compute the norm of the nth vector of my sequence. Of the nth vector of my sequence. To this nth, I just multiply the ket vector A dagger to the n on ket naught by the corresponding bra vector, that is not A dagger to the n. Now I can rewrite this expression in this way: A to the n minus 1, A hat, A dagger to the n naught. And now I can pull out this operator A to the right using the commutation relations for the operator A and A dagger. As we have found, A commutes with A dagger to the n to n A dagger to the n minus 1. So using this formula, I can proceed as follows. Notice that in the rightmost position, this operator A kills the ground state by the definition of the ground state. The operator A annihilates the ground state. So I left with the commutator alone. When I interchange these operators, the result is given by the commutator. So I get n not A to the n minus 1, A dagger to the n minus 1, not. So I get almost the same expression I have started with. The only difference that now I have n minus 1 instead of n, and I have this n in front of the scalar product. So I can proceed in this way once and again, and by simple induction I conclude that finally I get something like n factorial and scalar product of the ground state with itself. Okay, now let us suppose that the ground state belongs to the discrete spectrum and is normalized vector, so its norm is equal to 1. Then I can define the sequence, I can define the orthonormal set of vectors, which I denote by n, which are given by 1 over square root of n factorial A dagger to the n on ket naught, where n runs from 0 to infinity. And by construction, all these vectors n are normalized and orthogonal to each other. Why? Well, because they describe the states with different values of energy, so they belong to different eigenvalues of one and the same Hermitian operator, the Hamiltonian of the harmonic oscillator. So I have n times m is given by Kronecker delta and m. So they form an orthonormal set of vectors. And as we shall be seen in a while, actually these vectors form a complete set. So they form a basis in the Hilbert space of states of the harmonic oscillator. Let me denote this Hilbert space by H. So using this basis we can expand all any cap psi over the basis n with some complex coefficients Cn. Whereas the coefficients are just projections of their ket vector psi on the basis vector n. So Cn are just the coordinates of the vector psi with respect to the relative to the basis n, And of course, in order for this psi to belong to the Hilbert space, it has to have finite norm. The norm of psi is given by the sum of absolute values squared. So this must be finite number, absolute value squared. So regarding these coefficients Cn as coordinates of our vector psi with respect to the basis n, we can arrange them into infinite column vector. Let me write this vector as follows: C0, C1, C2, and so on. And by construction, this column vector defines a state of the harmonic oscillator, a state psi of the harmonic oscillator in the energy representation. Why energy? Because each basis vector is an eigenvector of the Hamiltonian. Each basis vector describes a state with definite value of energy. So we have energy representation. This is energy representation. The above operators A and A dagger are known in quantum mechanics, are usually called the raising and lowering operators. So A is a lowering operator, lowering, and raising operator. Also, they commonly called ladder operator or ladder operator or ladder operators. Ladder operators. The name ladder operators speaks for itself because the action of these operators increases or decreases the value of the eigenvalue of energy by a fixed amount, namely h bar omega, according to our computation. And this is very similar to what happens when you steps up or down steps. Each time your potential energy increases or decreases by a fixed amount, by a fixed value. And the Hilbert space, which is generated by the repeated application of the operator A dagger to the ground state, is known as a Fock space. Fock space. This is a name after the famous Russian Soviet physicist Vladimir Fock. Russian physicist Vladimir. Now let us see how these ladder operators, act in the energy representation. So we take an arbitrary ket psi given by its expansion over the basis vector and apply to it the operator A hat. Since A hat is a linear operator, we can write its action as A to n, and using the definition of the basis vector, so the ground state, we can proceed as follows. So here n from 0 to infinity, Cn A dagger to the n, square root of n factorial, on the ground state. Now I want to pull out the operator A to the right. So this operator A, when it hits the ground state, gives me R0, and I am left with a commutator of the operator A and A dagger to the n. So using my commutation relation, non-commutation relation for the A and A dagger to the n, I can proceed as follows. This is given by Cn n A dagger to the n minus 1 over square root of n factorial to the ket naught. Now it is convenient to shift the summation index n to pass from n to n plus 1. This gives me the sum over n from 0 to infinity, Cn plus 1 square root of n plus 1 square root of n factorial A dagger to the n on ket naught. So I see that this combination gives me the nth basis vector, so I can finally write this as sum over n plus 1 square root of n plus 1 Cn plus 1 n. And the coefficients in front of the basis vector are just the coordinates of the vector A acting on psi. So these are just the coordinates on the vector of the result of the action of the operator A on the ket sign. So we see n prime n. Now I see that from these formulas I see that the coordinates of the initial vector psi, that is C sub n, and the coordinates of the resulting vector are C prime n. They are related by the following equation. C n prime is given by square root of n plus 1 times Cn plus 1. Cn plus 1. And this formula shows how the lowering operator A acts in this energy representation. And similarly, we can find the action of the operator A dagger on our ket vector psi. Again, we apply the operator A dagger to psi. By linearity, this can be written as an infinite sum of Cn times A dagger on the basis vectors. And using the definition of the basis vectors of the Fock space, we can write this as A dagger to the n plus 1 over square root of n factorial on the ground state. ground state. Now let me multiply the numerator and denominator of this fraction by square root of n plus 1. Square root of n plus 1 in a numerator, and the same factor in the denominator gives me n plus 1 factorial. Here I get n plus 1 on the ground state. Again, I see that this combination of operators and factors gives me the n plus 1 basis vector, so I can basis vector. Now it is convenient to shift the summation index n by minus 1. So let me pass from n to n minus 1. Then I get infinite sum over n from 1 to infinity, Cn minus 1, square root of n, square root of n times n. Now see that for n equals 0, this expression vanishes, so I actually can extend my summation to 0, so I can sum from 0 to infinity. And again, writing this as C2 prime n minus Cn on n, I see that the coordinates of the initial vector psi and the resultant vector are related by the following equality: C2 primes n is equal to square root of n times Cn minus 1. And when I substitute here n equals 0, I get C minus 1. I haven't such coefficients, but for n equals 0, this factor is equal to 0, so I get that C2 primes 0 is 0. Okay, the action of the ladder operators A and A dagger becomes much more visual in matrix notation, and according to our calculations, the matrices of these operators in the Fock space are given. I have the following form. So let me write down the matrices of the ladder operators in the integer representation. For A hat we have an infinite square matrix with most of which entries are 0. The non-zero elements, they are located on the side diagonal. Square root of 1, square root of 2, square root of 3, and so on. And on the other places we have zeros. And the matrix for A dagger is obtained by Hermitian conjugation of the matrix A. So we just transpose this. We can transpose this matrix and get 0, 0, 0, 0, and so on. square root of 1, square root of 2, square root of 3, and so on. Everywhere there. Everywhere there. And in particular for the action of the operator A, lowering operator on get vector psi, this action can be written in matrix notation in the following way, as a product of two matrices, namely square root of 2 on C0, C1, C2, and so on. And multiplying these matrices, one can easily get that the result is square root of 1 times C1, square root of 2 times C2, square root of 2, and so on. In so doing, the eigenvectors of the Hamiltonian, they are given by the basis vectors of our space, our Fock space. Namely, the ground state is just the first basis vector. The first excited state with number 1 is given by 0, 1, 0, 0, 0, 0. Then we have 0, 0, 1, 0, 0, and so on. In particular, it is quite clear that applying the operator A to the ground state, that is to the first basis vector, we get 0. Why? Because substituting here 1, 0, 0, 0, we get C1 is 0, C2 is 0, so we get 0 vector. So indeed, the operator lower and operator A annihilate the ground state. It's the first basis vector of the Fock space. For the sake of completeness, let me also write down the matrices of the operators H, A, and A dagger. Well, for the operator, for the Hamiltonian, we have H bar omega A dagger A plus H omega over 2. So multiplying these matrices A and A dagger, we can reconstruct the Hamiltonian, but in actual fact, there is no need to make any computation, because we know in advance that in its own representation, the Hamiltonian is given by the diagonal matrix, and the diagonal entries of the Hamiltonian are nothing but the eigenvalues of energy. So we have immediately that this matrix have the following form: H bar omega is a common factor, and 1/2, 3/2, 5/2, 3/2, or and so on the diagonal. This is diagonal matrix. Diagonal matrix. And as for the operators of Q and P, that is operators of position and momentum of the harmonic oscillator, well, these operators are given by linear combination, according to the definition of operators N and dagger. These are given by linear combinations of these operators, so it's not hard to find explicit expressions for their matrices. let me remind you that according to our definition, Q hat is proportional to the difference of the operators A, dagger, and A, that is H bar over 2m omega, A dagger minus A, and subtracting two matrices for A dagger and A, one can find this expression square root of H bar over 2m omega. And here the matrix with zero diagonal minus square root of 1 minus square root of 2 minus square root of 3. And similar expression for the matrix of the momentum operator. This is proportional to the sum of raising and lowering operators. A dagger plus A. This gives us mh bar omega over 2 times 0, square root of 1, square root of 2, 0, square root of 3, and so on, and 0 everywhere of the diagonal. As a scene, the matrices for the operators Q and P are Hermitian. These are Hermitian matrices. As expected, it is also seen that the matrices Q and P satisfy the canonical commutation relation. So commuting these matrices, it is not hard to see that the result is proportional to the unit matrix. It's proportional to the unit matrix. They satisfy the canonical commutation relation. Finally, let me say a few words about the initial formulation of quantum mechanics as it was proposed by Werner Heisenberg in 1925. Heisenberg 1925. In the early day of quantum mechanics, the main problem was to identify and explain the energy spectrum of atomic systems. And the recipe formulated by Heisenberg for mechanical system with 1 degree of freedom was the following. First, find a pair of matrices, infinite matrices, P and Q, satisfying this commutation relation. Clearly, there is an infinite matrices satisfying this relation. Then substitute these matrices in the Hamiltonian of the classical mechanical system, which is supposed to be given by a polynomial in position and momentum, something like p squared over 2m plus some polynomial u of q. Finally, diagonalize the resulting matrix H. Then the diagonal elements of this matrix will give you the admissible values for the energy of a quantum mechanical system. This was a recipe proposed by Heisenberg. By the way, this is the reason why this early version of quantum mechanics was called matrix mechanics. Matrix mechanics. Matrix mechanics. And the above matrices for QT that we have found studying The harmonic oscillator provides us an example infinite square matrices satisfying these Heisenberg commutation relations. And these matrices for QP were chosen in such a way that the Hamiltonian of the harmonic oscillator up here is automatically diagonal, is given automatically by a diagonal matrix. If we were use these matrices for Q and P for some other Hamiltonian H, then this last step with diagonalization of the matrix H would be inevitable. Okay, I think it is good times to stop here. We will continue our discussion of the harmonic oscillator at the next lecture. Thank you for your attention.